Hey guys, this is Terrence and welcome to the new episode of RhinoPython GhPython Playground. And this is our today's pattern. It's kind of leaf growth pattern on some surface we provided. So I will bring up the sketch, the diagram to show how we can create this kind of pattern. This is a simplified version of our unit. So when I click in each of the curve, you will find all of the curve has the shared start point and end point. The only differences is that they have different handles, or more specifically, they have handles pointing at very similar direction but with different length. So these four things, these 2 points and 2 handles, are the essential components of creating a Bezier curve. So I just deconstruct these components and display it on this diagram. So we have point A, we have point B, we have handle A attached to point A, and we have handle B attached to point B. So if we line up these 4 points as point A, handle B, and point B, we will have this kind of Bezier curve. So this is the logic of creating a Bezier curve. The way of finding this handle is we can calculate the tangent vector of the specific position on our base curve or on our source curve, and we will see how to do this during when we are coding later in this video. Yeah. So yeah, I can click this one and just change the length of the handle, and you will see we will have pretty much different curve just by modifying the handles instead of modifying the endpoints. So here is how we can apply the pattern on our how we can apply the units on our pattern on our skeleton, I think. So we have our base curve, and we have 2 curves on each side for us to create the span of the leaf. So on our base curve, we will find a point located at the 0.0, which is a perimeter of the curve. And also we will find somewhere in our side curves, the position should be a little bit higher than the position on the base curve, I think. So we will have this kind of difference in height. And then just use these 2 points, we find the tangent vector of each point. Then we can generate this base unit. Then we just need to repeat this process. Then we can get a whole series of leaves, and we can also do the same thing on the other side. Then we will have the leaves growth in 2 directions. So let's start working on it. Here is the Grasshopper file, here is the Rhino file, and I have my code file here. So I drew some base curve here, and I think you can do this yourself. I think you can create your own curves yourself, but be careful. Maybe just as a start point, we do 3 curves. That would be easier. Yeah, because we want our pattern, we want our leaf grow in both sides. And I want to first connect this file to our GhPython node. So yeah, the first thing is I want to import these curves. I will use the curve nodes and set multiple curves, but be careful about the sequence. I will do this as first one, second one, and third one. So my base curve locates at the second one with index of 1. Sorry, and here I prefer to show code input parameter and input is path. Yeah, here is the curve. I will change this input to curves and list access, then change the type to the curve. Sorry. And then I will connect this Python file to our code input. I will do file path, synchronize it and choose an existing file located on my desktop. Okay, then I will temporarily remove this input. Then I will connect a panel here to see if if these two files are successfully synchronized. So I will do here, say, sorry, I should start atom listener. I should type start atom editor listener here, so I can have some autocomplete feature in my atom editor. I should say import rhino.geometry as RG, and at first I just want to print test to see are they successfully connected. So I say test here. Save it, and yeah, the test pops up here. So that means our first step is successful. It's a good start point. So I will hide these original curves and remove this one. So I think the first thing we need to do is sorry, my throat is a little dry today. The first thing is we need to find a point and its handle, right? So I think we first need to define a function called GetPointHandle, and with the input parameter should be, we should have a curve, and we should have a start parameter. I call it start t. We should have a handle scale, HNDLE scale, which is the length of the handle. And yeah, I just want to keep these three parameters here for now, and we can start extract the point. So instead of using the specific parameters, let me first show you what is the real domain and what is the normalized domain. The real domain is the curve.domain here, and I will print this domain equals to curve.domain. So I will print dom here, and I will call this function just behind the helper function section, which is I will put it far below here. So I will say get point and handle DLE, and now I just want to choose our base curve, which is the curves with the index of 1 start t. Okay, let's randomly put some value here. So I save it, and you can see here is the domain. It ranges from 0 to 19, and different curve have different domain. That's something pretty annoying. One thing we can make it simplified is we use the normalized domain, which is ranges from 0 to 1, and we can use a function to convert the 0 to 1 value to this 0 to 19 or 0 to other value, which makes our life very easy, and we can apply the same fraction. Like we can do the 0.2 here and 0.2 here, and I can make sure they are locating at a very similar position. So we will use the command called curve. Sorry, it's normal, MALIZED, normalized length parameter. Then we will have our start t. I will replace the start t here as 0.0. So here is the start t. And yeah, I think we have this. Then I want to change the name from DOM to PT parameter. So in this way, we will convert this 0 to 1 parameter to this 0 to 19 parameter range. I think we can just print this out. We can say PT parameter, and it's locating at oh yeah, the output are two values. The first one indicates is the conversion successful. The second one is the real tangent value. So we do 1 here. So we have our tangent value. If we change to 0.5, we will get this kind of 11.15 or something. So we can in this way we can keep finding a point in the range between 0 to 1. So the second thing is we need to extract the point, right? So we can say point equals to curve dot point at pt parameter. And also with this tangent with this parameter, we can also extract the tangent value, the tangent vector at that specific point, as we mentioned. So we can say vector equals to curve dot tangent at the same parameter. Yes, same parameter here. Let's just print it out and see how these two things looks like. Vector, yeah. So we have a vector here. This is a Rhino geometry, and we have a vector 3D. And the next thing I want to do is the tangent value. In most of the time, it's normalized, but we should avoid some very, very weird situations. So just for safe, we should unitize this vector, which means we set the length to 1. That is a normalized vector, and it will be easier for us to modify the length in the later process. So we say vector dot unitize, and now we have our base element. We have point. We have the tangent vector. The next thing is we need to find the length of the tangent vector, or the length of the handle, like here. Maybe now, because we are normalized, the length is somewhere here. But if we find the length, we can multiply the scale value multiply the scale value to the tangent vector. Then we will get a handle with some specific length. So we can do. So we first need to do is we need to find the real length of our base curves. So we do span equals to curve dot domain 1 minus curve dot domain main 0. Then we need to create an interval. We will create an interval, use this hand scale here. So we say interval equals to rg dot interval, and with the pt parameter and pt parameter plus handle scale, then we will have an interval. This is quite weird because we are using the Rhino geometry. In Python, we can define any interval like 0 to 1 as a list, but because we are using a Rhino geometry, which is like C# based library, so the interval shouldn't represent it as list, but represent as the interval class. So this is why we do this thing. And here I think as we have our let me see what we can do. As we have our point, we have our interval. Oh yes, I need to update this handle scale here. So maybe now I can say the handle scale could be 0.2. That means 20% of the total length. Sorry, let me think about that. Yeah, which means the 20% of the total length. So we will have a handle with a length of 20% of this base curve. So we have our interval. So we should convert the interval to a length. We will use the function called scale equals to curve dot get length. and place this interval into this parenthesis, then we just need to multiply this scale value into the to the vector, to the unit height vector. So here is the scale. Then we can just return this point and handle here. So let's see, is this work? Interval. Save it and handle. Oh, sorry, I'm so stupid. It should be vector. Yes, these two things are returned, so we can just say A equals to this, and oh, yeah, the start point of the curve actually is here. So maybe I can just reverse these curves, make the start point start from here. So I can say reverse. No, it's flip. It's called flip curve. Yeah, the start point is now here, and let's see what is the second thing is it's the handle vector, and how I can visualize this. I can do like b equals to a0 plus a1 and save it. Then we will have this handle, but this one is too small, obviously. Maybe I made some mistake in setting this hand scale. So let me double check this thing. Domain 1, pt parameter plus handle scale. Let me make it larger, like 3. Oh yeah, it's bigger now. Okay, so I made some mistakes. pt parameter is the normalized one. So why don't we print this interval to see the actual value here? V. It ranges from -19 to negative. It's kind of weird, but +3. (2.0). Okay, I just figured out that actually here the handle scale, in handle scale we should provide some real length instead of the fraction length. If we provide 2.0 here, that means the length of this vector is actually 2.0. So yeah, so here is the mistake I made. And then we have this first one. We have these first 2 points. Maybe we can do the same thing on this on the left side of our base curve, on this curve. So we just replace. Let's see. We just replace handle. Where is the handle scale? Okay, the next thing is we can generate similar 2 points here to test out our first set of Bezier curve. Sorry, so we can do maybe like b equals to get pt and handle with curves 0 and input. Maybe the start parameter might be 0.2, because in our diagram I show that I prefer to set this point a little higher so we can create this kind of curve. So we do this, and point A, point B, we can set the length as 2.0 as well. But this time, because I want the tangent vector at the side curve pointing at the reversed position, so maybe I want to put another parameter here called reversed. By default, it's false. F-A-L-S-E. By default, it's false. But when we make it true, we should reverse the tangent vector. So here we can say if reversed and vector multiply equals to -1, which is reverse. And then we can just add the vector to the point. Then we will have the handle. We will have the handle points here. The handle point here. Sorry. So we do handle equals to point plus vector, and we do handle here and save it. I think there is something wrong here. If reverse spelling issues. Yeah, we have this one, and we will have another one on our B end. But why it's not popping out? Let me see. Okay, so actually, I shouldn't reverse all of the curve. I just need to reverse. I can just modify those things in my Rhino workspace. I can do show, and I don't do the reverse at all. I think I just need to let me check the direction of the third curve. Yeah, it's right. So we just need to reverse the curve in the center, which is our base curve. I can do flip. So we will have our points in the right position, and I hide them again. And this time we have this 4 point. We have point A here, and I think this is point B. We have handle A. We have handle B here. Then we need to convert these 4 points into a Bezier curve, right? So let me do this here. I want to make a comment at our first function. To make it clear, I say step 1, generating PTS and handles. Then our step 2 is gonna be generating NURBS curve. Not NURBS curve. It should be Bezier curve. And we define another function called gen, Bezier CRV, and we put our point A, point B, handle A, and handle B. Then just right behind here, we can just call rg.bezier, Bezier curve. And let's test one thing, that if we can just make these 4 points into a list, then put it into this Bezier curve function. And there is an error here, but I want to just show what error we will encounter if we do this. Handle A, handle B, and PTB. So we can say Bezier curve equals to this one, but there's nothing wrong here. Oh, it seems pretty good. Maybe because we haven't called it. We haven't called a function. And here we can change it to A equals to PTA, handle A equals to this function, and PTB, handle B equals to this function. Then we can say A equals to generating Bezier curve, and put these 4 points into this function, into the parentheses of this function. Handle A, handle B, save it, and yes, it should be an error here because there's another value type conflict. It shows this enumerable here. In most of condition, we can just use the Python list to represent this numerable. But in this specific function, we need to convert the Python list to the enumerable. Sorry, it's so hard to pronounce. I can just call this kind of list is a C# list. So in this specific condition, we should first convert this kind of point list structure to a C# kind of point list structure. So we need to add a line of code here. We should say PTS equals to. Oh, we should import another library called import rhino.collections src. This library will help us convert anything like curves points into the C# list. So we can say pts equals to rc dot point 3D list, and we just put these 4 points into this point 3D list function, and then say pts here, and the arrow disappeared. I want to remove this print function, print code here, and then maybe we can just return this Bezier curve to see what else we should do to visualize this Bezier curve. Because for now, you can see, although we have our Bezier curve here, I want to connect this panel here, and you can see we have our Bezier curve here, but although it shows here, it doesn't show up, or it doesn't appear in our Rhino workspace, because the Bezier curve now is invisible. We should do one more thing. We should convert the Bezier curve into a NURBS curve. Then we will see what that curve looks like. So we say Bezier curve equals to Bezier curve dot to NURBS curve. Save it, and it's here. Now I think, here sorry, my Siri just recognized, just falsely recognized I'm calling her, and I will replace this to say true. So here we have our first Bezier curve, and maybe now I can just create 2 inputs for each of the handle scale to create a kind of modifiable or varied input for each of the Bezier curve. I mean, I can create 2 parameters to control the value or the length of both handles. So I do like, let me make sure the name of the parameter, it should be a factor set it as a float value, and set another one as b factor BFAC. And now I want to make the a factor as 0.05 maybe. Then the b factor could be 0.2. And now we replace these 2 values. Sorry, it's not here. It should be here. We can replace these 2 values as a factor and b factor. Okay, so this might be something wrong. Oh, they are too small. Yeah, I should say 0.5 and 2.0. A, B, yes, and we have this one. We can modify these 2 values to see how they works. Yeah, I want to keep it like maybe 1, and keep another one like 4.1. And now what we need to is we need to create 3 sets of the factor combinations. Then we can create 3 curves for just one leaf unit. So we need to create another function called generateleaf. We say step 3. We can say this function, we can comment this function as creating leaf EAF, and we define the function as genleaf, and we input our curve A, curve B, and our A parameter, which is the parameter or the parameter value located at curve A. The second one is B parameter, A factor, and B factor. So inside here, we first declare an empty list called curves. I should say curves, yeah. And we say the count. That means the number of curves in each of the leaf set. Maybe it could be 3 for standard, but it could also be 4 if we want to make it more complicated. So I do like count equals to rand integer, ranges from 3 to 4. And I should also import the random library here. I should say import. Sorry, I should say from random import rand int. Save it, and then we can loop over this number. We can say for I in range count. So the minimum factor should be minimum factor could be just a factor, and the maximum factor could be the b factor. And maybe we can make it more varied by adding a random function, adding it to a random number, like we can say minimum factor equals to uniform a factor plus a uniform uniform a factor to a factor plus 0.5. I just set it as 0.5, and we can see if this value too large or too small. Then we can modify it later, and we can do the same thing here. We can say b factor plus 0.5. Sorry, it should be 0.5 here, and we should also import this uniform function into our workspace. So we say uniform form here. Then we have these two factors. We need to create a scale, create the scale list. So we say scales equals to minimum factor and maximum factor. Then first we need to find the handle A and handle B, right? The point A, point B, handle A, and handle B, right? So we do point A, handle A equals to, what's the name of this function? GetPointHandle. Here, and we place curve A here, a parameter here, and scales 0 here. Then we do the same thing to generate the point B and handle B equals to get pt and handle curve B parameter and scales 1. Yes, and then we can use these 4 points to generate a Bezier curve. So we say curve equals to generate NURBS curve PTA, PTB, handle A, and handle B. Then we just append this curve to the curves list. So we say curves.append CRV. Then at last we return curves, and let's see the result of this function. Let's just test it, and we can say A equals to generate leaf curve. Make it curve. Curve 1 is our base curve. Curve B is our left side curve. And A parameter this time I just say 0.0, and B parameter 0.2, and then A factor, B factor. Save it to see what's wrong here. What's going wrong here? Curve is not defined in the line 49. Oh, sorry, it's curves. Save it. Uniform FORM, it should be 36. My spelling problem. Generateleaf curve is not defined. Oh god, this should be Bezier curve, I think. Okay, so and here is something. There are two things we need to modify here. The first one is we need to place a true to true place a true to this end. And the second thing is you can see now they are pretty close. I want it I want it like looks like this kind of shape. So basically we want if we can see this the difference of the handle length between these two curves, we will see in this curve the handle A is longer than handle B, while in this one the handle B is longer than handle A, and in this one they are pretty the length of both handles are pretty close. So I want to add some codes here to create this kind of effects. So I can say if I equals to 1, then we swap the minimum factor and maximum factor. That means basically we swap the length of these two handles. Like in this curve, this handle maybe the length is 2 and this maybe just 0.5. And for this one, we can just swap them. We can make it as 2, but make it as 0.5. So this is the reason I inject this code. I can say scales 0, scales 1 equals to scales 1 and scales 0. This is the Python way of swapping the value inside swapping the value. Yeah. And then if I is larger than 2, we make the length of two handles pretty similar or pretty close, so we can make a Bezier intermediate Bezier curve between two bound curves. So we say mid factor equals to minimum factor plus max factor divided by 2. Then in this condition, scales 0 could be uniform. Like uniform, I can say mid factor minus 0.5 maybe, and mid factor add 0.5, and do the same thing on the scales B. Scales 1, scales with index 1, sorry. So we have these modifications, and we can see now we have this kind of pretty decent leaf shape. If we are not satisfying with this kind of shape, we can just modify the A factor and B factor value here to see how we can use these two inputs to modify the shape and make it become our satisfied make it become more satisfied. And I find there's one more thing I should do, because every time I change this value, the program generates a completely different iteration of the curve. So I want to make things pretty consistent. So I want to set a fixed random seed. So every time we generate the same result, and if we change this value, we can see how the value affects on that specific iteration. So we do this like import seed to our workspace, and we can say seed equals to maybe, sorry, it should be a function seed. Maybe we can set it as 200, and then if we modify the value, we can see how these two values take effects on this just specific version of leaf. I think so. We already construct the very basic unit of our pattern. So the next thing is we need to apply this. We need to apply this unit to the whole curve, to the whole base curve, and to both sides of the curve. So I think we should do it down here. maybe I will put a comment to separate these two parts, and to avoid messing these two parts of code. And here I prefer to say these are helper functions, GLPR functions. And here we can just say program, or some better name you can come up with, program. So let's see what we can do with this. I think the first thing is we need to define the step. We need to define the step of each iteration. Like this ranges from 0 to 1. Maybe if we can define the step as 0.1, so then we will have nine leaves along this curve, like 0, 0.0, 0.1, 0.2, 0.3, 0.4, 0.5 until 0.9, but we can't do it on 1.0 because it's the end. So we should first add another parameter. We can say like this could be, we can say this as the step, right? And set it as the float. So we can define the step of repeating this base cell. So the step could be 0.1. And inside our code this time, I want to first convert. Okay, so let me first do this. Then you will understand why I need to convert this step value from the percentage value to an integer value. So I do like parameters equals to maybe I for I in range like 0 to 0.0 to 0.8, because I want to set the start point of the left curve as 0.2, so I can't set it to 0.9, because in this condition this value on this curve is gonna be 1.1. It's already out of our boundary, so I will set it as 0.8 with a step of 0.1, but with a step here. But actually it doesn't work because the range only accepts the integer value. It doesn't accept this fractional value or this decimal value. So we need to do something like range from 0 to 80, then with the step. So we can set the step from 0.1 to 10. So it's basically 0, 10, 20, 30, 40, 50, or something like that, just so on and so forth. So I need to convert 0.1 to 10. That is, we need to multiply this value by 100. So we can do step equals to integer step multiplied by 100. So we make sure this is an integer value, and we make sure this list comprehension functions well. So we do b parameters equals to I for I in range 20 to 100. So they will have a 0.2 difference in the position. Then we do the step as well, so we can just print these two values to see how they looks like. A parameters, b parameters, save it, and here you can see from here to here is our target parameter on this curve, our target parameter list on our base curve, and from 20 to 90 is our target parameter list in this left side curve. So yeah, we basically have our parameter list here. So we need to create an empty list to contain all of the leaves. So we can say leaves is an empty list, and maybe yeah, we just do the leaves for now. So here we use loops to loop over all of the parameters in this list. So we do for I in range for I in range length of a parameter. Then we can just extract the parameter using the index. So we do a parameter equals to a parameters with the index of I, and b parameter equals b parameters with index I as well, because the length of these two lists are consistent. Then we can do like leaf left. Let me see. No, we just need to do like let me see how. Yeah, maybe we can just stick on this side, and we can do this side later. So we do like leaves. We can do leaf equals to generate. What's the function name? Oh yeah, generate leaf here, and we can input our we can input our curves into this function. So the first parameter is gonna be curves 0, and the second curves 1, and here's curves with index of 0. Basically it's quite similar to here, but this time we will not use these two values. And for the parameter A, we will put a parameter here. For the parameter B, we will put b parameter here, and a factor, b factor. And then after generating the leaf, we can just input the leaf. We can just append the leaf into the leaves list. So we can do leaves.append leaf. So first, let me save it and see anything's wrong. Yeah, I always make this kind of spelling problems in line 65, a parameters. Okay, so let me try to print out the length of leaves. Okay, you can see it's keep adding leaves. So I think the leaves variable now is containing all the leaves we need. We can just replace this function with leaves. Then we can assign these leaves to the variable a, which is the output of our RhinoPython node. Save it, and oh, where is our okay, I know this is another problem we need to address, but it's minor problem. You can see this is an IronPython list structure. So basically, we need to convert this list structure, the Python list structure, to the tree, to the Grasshopper tree structure. That requires us to import a new library, which is import GhPython thon library dot. Yeah, it pops up. It's tree helpers as th. Then we can just do th dot list to tree, because our current value type is list. We convert it to the Grasshopper tree and we save it. There's a lot of problems here we need to address. The first thing is why they are connecting in this way. Let me see. Steps. Oh yes. Parameter A, it should be converted back to the fraction value. Sorry, I forget this step. This is so essential, but I'm so ignorant. Yes, and now we have our first set of leaves. Maybe now I can try to modify this step value to increase the distance between each leaf. So I can do 0. It can range from 0.1 to 0.10 to 0.30 maybe. And let's try how this one works. And you can see now we have, if we as we increase the distance, we will have the we will have the leaf we will have the last leaf on our stem. But if we decrease this value, we will have more, and the space is getting narrow, but the shape looks not so preferable for now. And I find the distance between these two curves are too close. So maybe I can modify the value here. I can set this mid factor minus maybe 0.0. 0.7 to, yes, minus 0.7 to 0.7, and it's still small. To 5, let's do it pretty large. No, just 1. Let's do it. Let's modify the value to 1, and maybe we will have a larger space. If 3, yeah, it looks pretty. Yeah, now it looks pretty. I mean, the distance is pretty obvious, but still too much. Maybe just keep 1.5 and 1.5 and 1.5. Just make it something between, and maybe we can add another input as the random factor, as the random seed. So we can say this as a R seed and convert the type to integer. Now we set it as 1000. The random seed could be pretty large. So I replace this value as R seed, save it, and now I can keep modifying this value to see different iterations until find one that I really satisfied. Yes, here is another problem at the end of the branch, because as you remember, we basically calculating the tangent value based on its length. Let me just move to somewhere here. Yes, when we are trying to find the scale value, we basically use the interval. So when the parameter is pretty small, like the stays in 0.6, when it's adding some handle scale, maybe 0.6 add 0.2 equals to 0.8. The 0.8 is still stays in the domain of 0 to 1. But when something comes to here, like if this time the point parameter is 0.9, when it adds some value like 0.2, it's gonna be 1.1 is already outside of 0 to 1 domain. So in this condition, that will only return the distance of this small fraction as the handle length of this point. So in this condition, we need to avoid this small handle scale that requires us to maybe somewhat reverse this interval from this one to this one. So let me just modify this here, and I can actually add some lines of code in somewhere just below the interval. So we say like if the interval 1 is larger than curve.domain, which means when the interval value is already outside of the domain, then we just do something reverse, like interval equals to rg.interval pt parameter minus handle scale yeah, and then pt parameter. So we basically reverse the domain, reverse the interval from here to somewhere behind it. So if we can save this, we can see, okay, this problem addressed. Then the next thing, we can just start to loop over all the curves. Then we can create curves, create leaves on this side and create leaves on this side as well. So we need to wrap this loop into another loop, which is the which is a loop that looping over all the curves. So I want to replace this I with J, because I want to make the major loop the major loop. I want to use I on our major loop. So I can say for I in range length curves, and add some indentation on these codes. Then we can do like it shouldn't be just one by one loop. It should start from like one, and the end is the length of the curve, and the step is 2. So we basically just, if we have more curves, we just looping over every other curves. Then that means we just loop over our base curves, but neglecting the side curves, which is kind of assistance for us to creating the leaf pattern. Then we can extract these kind of assistant curves. Inside here we can say current curve is the curves with index I, which is the curves we are looking over. And we can do like left curve CRV equals to current equals to curves with I minus 1. It's the curve on the left side of our base curve. And maybe we can do the right curve equals to curves I plus 1. But in some conditions, if we have even number of curves, like maybe I can do like I can add a curve here. I can add this one too here. Then we have even number of curves. When we are on this base curve, we have both sides of assistant curve for us to create leaves. But when we are locating at this one, we only have our left curves. We don't have our right curves. So in this condition, this line of code must be returned some errors. To address this problem, I can say like indentation. I can say like try right curve right CRV equals to curves I plus 1. If this doesn't work, we say except we assign the right curve as a non-value. So I think let me just modify the shape of this curve to make it match the flow of our curve combinations. Then I will reassign all those curves into our curves container. We can do this and hide it. Then we have our left curve. We have our right curves. Left curve here. We have our right curve here. We have our left curve here. Even if we don't have our right curve, we still have a non-value, which is easier for us to create some conditions to avoid creating leaves on the non-side. So we have this now. We need to modify the second loop. We need to modify the inner loop. We can say left. We can just modify this modify this to left leaf equals to generateleaf function, and the first input parameter is gonna be current curve CUR. This should be current, and the second input is gonna be our left curve. So we will have our left curve still. What is going wrong here? Leave append, leave left append. Let me check this back again. I think there might be something wrong happened here. Left leaf equals to, yes, actually we have our the parameter value here. We still need to modify these two values. Is a parameter j, b parameters j. I don't think it's wrong. Okay, so let's first print out our parameter list to see is everything correct inside here. And I can connect a panel input here, a panel node here. It's not wrong. 0 to here, 0 to here. And if we just bake it, let's see what's the problem inside here. Bake it and see. Yes, they are all generated in the same position. So this is something I need to avoid. It's so tricky. Lives here. And parameters here. Current curve is this one. Left curve is this one. A parameter is this one. B parameter is this one. Append leaves. Okay, so just let us revert to our previous set, and I think in this condition we might generate something right. Still wrong? Okay. If we comment this out and make it back, we say curve see your vs 1, CURV as 0, save it, and okay, still the same. I have a feeling that maybe the program crashes. Cancel. Okay, so we can see the leaf is not defined. Oh yeah, the problem is here. Yeah, the program just crashed. Just crashed. So we don't get the right result. And I just fixed it. Left leaves. Yeah, we have this one. So because I forget to replace this name, replace the name inside this parenthesis with this newly created one, so we didn't get the correct result. Now we have it. We can just keep going. The curves is gonna be okay. Let's still do this. Nothing wrong. The curve's still gonna be the curve's gonna be current curve, and this one's gonna be left CRV, and we have this with no problem. And we do the same thing on the right one, so we can say if the right curve is not none, so we say if right curve is not none, we do the leaf, we do the right leaf equals to generateleaf. This function with current curve and the right curve, and everything remains unchanged. Then we can apply this. We can just append this right leaves. Now it's it's not singular value. It should be the plural or something. we append this right leaves to the leaves list. So we can say leaves dot append right leaves. Save it. See the result. It's gonna be some problem take place again. Let me double check this one and see what's going on here. Leaves right curve. Did I make the same mistake again? I don't think so. We have we have repetitive curves here. So basically on the left leaf, we made some mistakes. Left leaves, oh yeah, VES. Okay, so we addressed all of the problems. Now let's see if we increase the number of curves. Can this program running well? So actually I can show all the curves and say set multiple curves 1, 2, 3, 4. Yeah, it works. What if we create more curves? I think the result will still be correct. And we say set multiple curves 1, 2, 3, 4, 5. Okay, so basically we have our pattern. Now we can play with these values to see how these values will affect the look of our pattern. If we have a smaller a factor, we will have the leaves looks very round, and increase it will make the leaves pretty thin. Increase here, the leaf will looks pretty wide, and decrease it, the leaves become pretty thin. So here is how we can use these parameters to modify our pattern. And here is the random number. We will have different iterations or different version of our pattern. So basically we have our pattern here today. Let me preview off this one and hide it. So here is our leaves. And yes, that's it for today's video. Thank you so much for watching. If you have any comments, any thoughts, or any concerns, please leave comments below and let me know. I will try my best to answer each of your concerns. And yeah, that's it. Thank you so much for watching. Bye bye.